Good afternoon and welcome to Year 11 Physics. Today we are going to be looking at momentum for the first time. And to kick us off with momentum, we're going to have ourselves a little bit of a fun time, a bit of a play time, a bit of a muck around. And yet it's not really a muck around. We're trying to build intuition. In physics, in classical physics like this is, when you do a calculation, when you do a problem, your understanding or your gut feeling about what the answer will be is very often exactly what the answer will be. You've been alive for 16, 17 years. You guys have been alive for 16 or 17 years. You've seen things moving around. You've been in cars, you've been on bikes, you've been on skateboards. So when you do a calculation, if you get an answer which just feels wrong, it probably is wrong because your intuition is actually quite reliable. We're going to have today a little activity at the start of the lesson to build intuition regarding momentum. We're going to be using these trolleys here, these trolleys. These are trolleys which have very, very nice bearings on them. And the intention of the trolleys are to have them glide across the floor such that they largely act as if they were frictionless. Some people call them crash carts. Some people call them frictionless trolleys. Okay, some people call them kinetic carts. Now, the kinetic carts have these very, very nice bearings. You will not do what some of my students did at another school that will remain nameless. They are not skates. Okay, so when they go on the floor, they don't go on the feet. If you do that, you break them. They're actually quite expensive. So we don't want to do that. Now, we have also here, we have a rod which is mounted on a spring inside the crash cart. Now, when the crash carts are working really well, you can actually load the rod, and you've got yourself a trigger. There's the trigger. You press the trigger, the rod shoots out. Okay, so there's all sorts of fun. We won't need to use the trigger mechanism today, but we will be using the spring part of the rod. We're going to start today with 2 of these trolleys. Oh, incidentally, when you use these crash trolleys, these kinetic carts, you will always place them, if you're not using them, you place them upside down, wheels facing up. That's how we store them, okay? For our little game of intuition, we're going to start with 2 trolleys, and it's just about absorbing and noticing and feeling and seeing what's going on. We are going to have trolley number 1, and we'll have that one set up, and we will have that one's going to be sitting there. We'll have trolley number 2, and we will have the spring of trolley number 2 facing towards trolley number 1. So this will be trolley number 1, trolley number 2. Trolley number 2 will start out with, U equals 0. Trolley number 1 will start off with U equals that way at some speed, some reasonable speed. It's not a competition. Okay, we're not trying to shoot them out the room. So we'll have the spring on this side so that the flat side of trolley number 1 hits the spring there. What I want you to do is just get the feeling of the trolley moving towards trolley number 2 and see what happens when they collide. The spring will help you to replicate an elastic collision. Okay, I don't know if you know what I mean by, like, think billiard balls, think pool balls, think bouncy balls, an elastic collision. So that's going to be our first thing we're going to do today. We will then, at a later point, have them face both of their springs away. Now, you don't realize this, but the trolleys have Velcro. So we've got soft and hard Velcro. So when two trolleys bump into each other, the Velcro are lined up such that they stick like that, okay? So that will be then a non-elastic collision. See, it'd be interesting to see what happens there. So to start us off with today, you'll find the trolleys behind William in that cupboard over there. I'd like you to work with your mates. Let's try not to have a big group of five people. Maybe have a group of 2 and a group of 3. Get a couple of trolleys out for each group, and just try different orientations to see what happens when they collide at different speeds. Maybe one's stationary, one's moving. Maybe they're both moving. Maybe they're moving towards each other. Maybe one's moving slow to one side and one's moving fast towards it. Grab a couple of trolleys, just get a bit of intuition for how it all works. Go. So we're going to muck around with the conservation law of momentum, but it's nice to know where momentum comes from as an idea. Momentum as a concept for us, the feeling of momentum is the tendency for an object to continue in its line of motion. So an object which has mass, it has velocity going in a direction at a velocity. It's the tendency of that object to stay at that speed in that direction. And what affects it, as you get the intuition of mucking around with things that move backwards and forwards, you play catch with a tennis ball, you play catch with a baseball, a very different experience. You play ping pong or table tennis, very different experience. The ball goes backwards, forwards, very easy to change its motion, change its direction. But when we start mucking around with passing a medicine ball, you go to the gym and you start mucking around with a medicine ball, it's much more challenging to change the velocity of a medicine ball. So you start to get the gut feeling, the intuition that mass is important and also that velocity is important when it comes to momentum. So let's look at where momentum comes from. So Newton's third law tells us that for every action, there's an equal and opposite reaction. Therefore, when one body interacts with another, the force experienced by the one is equal and opposite to the force experienced by the other. We've been talking about those action-reaction forces a little bit lately. So the force, if I've got my two hands pushing against each other, the force on my left hand due to my right hand is equal and opposite to the force on my right hand due to my left hand. Now, let's look at that. Force 1 equals negative force 2. But what is force according to Newton's second law of motion? That's Newton's third law of motion. What is force according to Newton's second law of motion? Force is equal to mass times acceleration. Let's put that in. So M1A1 is equal to the negative M2A2. How do we define acceleration? Acceleration is the change in velocity over time. So you've got two bodies that we're interested in. The force on one body, the force on the other body, the opposites of them. Look at the mass of one body, its change in velocity over time, the mass of the other body. You'll notice that time doesn't have a 1 or a 2 subscript, because this interaction is the same time for either body. So time is universal in this. It's absolute. That will not be the case about this time in year 12. If we cancel out the time, that allows us to multiply out the brackets, and we get M1V1 minus M1U1, where V is the final velocity of a body and U is the initial velocity of a body. That's equal to M2U2 minus M2V2. Which means we can say M1U1 plus M2U2 is equal to M1V1 plus M2V2. Now, we just said a few minutes ago, we said, hey, momentum is the tendency for something to keep doing what it's doing, keep moving forward. That's what we said. We said that the mass of it is important. We said the velocity of it is important. So look at that equation there. Momentum, M times U. That is momentum. M times V, that is momentum. That is what momentum is. It's the mass of something multiplied by its velocity, how fast it's going. That's what momentum is. So the units for momentum are kilograms, meters per second. The only difference between U and V is U is the speed before the interaction, and V is the speed after the interaction. That's the only difference there. So M1U1 plus M2U2 is equal to M1V1 plus M2V2. So mass times speed, mass times velocity, that's momentum. So we've got on the left-hand side of our equation up here, we've got all the momentums before the two bodies interact with each other. And that equals all the momentums of the bodies after they interact with each other. So the momentum before is the momentum after. The momentum before is the momentum after. Now, you were just mucking around with kinetic trolleys, and I saw what some of you were doing. You'd make one kinetic trolley move towards a stationary kinetic trolley, and then after the interaction, the stationary just basically swapped. It had speed, and then the formerly speedy trolley had none. Now, if momentum is mass times velocity, you could easily say that the mass and the velocity before the collision is the same as the mass and the velocity after the collision. If you use the Velcro connectors as you sent the two trolleys together, if you use the Velcro connectors as you sent the two trolleys together and the two trolleys stuck, then the total speed afterwards, if you sent one trolley into a stationary trolley, the total speed afterwards was much slower, but the mass was double. So this is leading us towards the conservation of momentum. Let's have a look at this. Now, actually, we're not going to do that right now. What we are going to do, cancel out of that. What we are going to do, we are going to go and have a bit more of a muck around with the PhET, the PhET Collision Lab. So what we might do for the remainder of this lesson is start building up those intuitions with the PhET Collision Lab. Let's see what sort of activities we discover. The PhET Collision Lab. There's 1, 2, 3, 4 different options. Two bodies moving towards, you can control how fast they're moving towards each other with these vectors. You can control that. You might have, okay, no velocity, no mass, whatever it might be. Click in here, change it to anything you want. Change this one to whatever you want. Okay, move this guy out, line him up, and just shoot him, see what happens. I'll let you guys play with that. We'll muck around with that for the remainder of the lesson. We've got about 5 minutes left.